Computer. Okay, so we're recording. All right. So, how do you guys feel about last week's exam? Uh, was it easy, hard? You got enough time? Any comments, suggestions? We're probably gonna end up doing the same for the final. So, any suggestion will help you will be very good. Any questions regarding homework? Any other things about last week's exam? Is it okay? Is it hard? Difficult? Time-wise, do you guys feel you have enough time? No answers? Anything? Okay. Did enough? Okay, I got one. Have enough time. Could have used more time. Okay. We agree on that. Need more time. Okay. Do we need more time on that? Okay. All right. So if we all feel like we need more time, we're probably gonna increase the time for the final. Okay. But again, the purpose having that in a specific time to basically put you in an environment where you have a normal stress condition where you work in the office. Okay, so that was the reason behind it. But yes, we will try to increase some amount of time for the final exam incoming a final. Okay, all right. So let me general comment on it. I look the whole submission overall there are 61, which is pretty good. And I got in the late submissions. There is one lady, I think she or he submitted to the wrong exam. Um, I don't know what happened there, but most of us are okay. And also, I looked over on the overall results. I think we're not doing too terribly bad. Overall, it's pretty good actually. Now, uh, about the time, I think everybody finished it on time. I don't see anybody have missing any blanks or have a very short answer to the problem, especially on the solution part of it. So I feel pretty good after looking through them. And I'm in the process grading them. And I shall be done by this Wednesday, and we can go over quickly over them in a Wednesday or a Thursday session where we have some overtime. Now, again, tomorrow, Tuesday afternoon, 2 o'clock, tomorrow, 2 o'clock, let me repeat, we're going to have some Q&A sessions where I'm going to walk you through some of the examples from the homework and from this course. Uh, that's another thing observation I have from the exam. I felt like we could all use a little bit more practice. Um, not that we don't have enough. It just I felt like we could utilize this online platform so we can do a little bit more. So Tuesday, 2 o'clock tomorrow, which is office hour, I'm going to illustrate some example problems. So hopefully you'll be there. Okay. All right. So that's it for the exam. Like I said, I'll finish grading by Wednesday, and maybe we can walk it over them on Wednesday or on Thursday afternoon. Okay. So sit tight there. Now, about the course, the last course day is May 8th, which is next week. And we have 2 full weeks. And in these 2 weeks, there are 2 content we cover. One is column, and the other is the development lens. Now, we'll see how far we can go, but so far I feel pretty confident finishing them all. And also, we might have a little time for review. Now, if not, I might want to do a survey to see if you guys like additional review in a dead week or not prior to the final exams. But that's up to you guys. If you guys don't have time, I can also record a video, upload to the YouTube channel so we can see it whenever needed. Okay, so no rush there. So we're pretty good on schedule with all the course content. Now about the final exam, considering we have changes during the semester about the dynamic thing, now there's some disturbance with the scheduling. And now we had our second exam a little bit late. I feel like we don't have enough of, how to say, we don't have enough for the final to do a cumulative. Because if we do a cumulative, there'll be a lot of problems where you need more time. And this take-home format is really bothering me on that. So what I will probably do is do a segmental. We'll do a little bit of a conceptual problem overall, but the solution will be focused on the final part of the lectures, which include the serviceability, which we'll finish today, and we'll talk about the short column, long interaction diagram for the regular column, and also a little bit develop the lens. So that's the main part the last exam is going to cover. So now hold on, don't share reflection anymore. Okay, all right, so that's a quick review of what we have done and a little bit future look for this next 2 weeks. Okay, so let's get back right into it about the serviceability. Okay, so about the serviceability, we have talked about the transformed sections, right? Transformed section means the correct section and how to calculate the moment inertia for that, and how do we calculate moment inertia for a beam in the continuous setting. And also we are talking about how we calculate deflections, and we ease into an example of showing you this is the structure. I have reinforcement inside the beam, the column joints, and calculate the applied moment diagram, and also calculate the transform section. We divide them in the positive moment region. Positive moment region is actually here. Okay, so let me zoom in a little bit. So positive region is roughly here, right, in the middle of it, and negative region roughly here. We're near the joint, right? So these are the positive negative region. The only reason why we differentiate them because they bend in different directions. So the compressive zone is on a different side. The compressive zone is on a different side, right? For instance, if we're talking about positive, the compressive region is on the top within the flange, and we have the converted transformed area from reinforcement at the bottom here. And with the negative moment, right? We take the compressive region at the bottom here, and then the tensile will be actually on the flange, okay? So these are how we differentiate the positive and negative moment region, okay? And you can see how we calculate the transform section, IG, and how we calculate the effective moment in terms of the cracking moment, applied moment, and also IG, the gross moment inertia, and the crack moment inertia. This is for positive region, okay? So we're gonna continue now for negative region, right? For negative region, what we're gonna do. So let me use different color. So for negative region, for negative moment region, which is the end, right? So IG is actually 17200 inch 4. Okay, so one thing I want to point out, now this number, this 17200 inch 4 is different from this number previously, okay? So what is different? Now, in this case, for negative region, right? For negative region, my T-beam is gonna have a shape like this, okay? T-beam is gonna have a shape like this. And when I do positive, right, I use the flange. But when I do negative, so this is for negative, I'm only using this right here. Only using this right here, okay, this right here, okay? So when I calculate IG for the negative region, right, IG for the negative region, I'm gonna use 1 over 12, right? And this is 14 inches, okay, and 14, and multiply by 24.5 to the power of 3. But what is 24.5 in our problem, right? Now look, 24.5 is the total height, of the beam, So in this case, we're talking about the total height of the beam right here, 24.5. Okay, so now you see, if we calculate the gross moment inertia, it's a little bit different already. Okay, so the cracking moment, correspondingly, let me just wipe the color out. The cracking moment corresponding MCR is going to be FR modulus of rupture, IG. Okay, let me just differentiate by putting a negative sign on top of it. Okay, and YT. All right, now this is 7.5 square root of 4,000 psi concrete strength and 17200 inch to the 4, and then bottom here is 12.25 inch. Okay, so if you wonder where that 12.25 coming from, this is essentially half of H. So that is 24.5 divided by 2 is 12.25. Okay, so that's where they come from. Okay, so now I have my cracking moment, which converted back to, well, first of it's inch in terms of pound inch. So this is 6 6014 pounds inches, So that is 55.5 kip feet, 55.5 kip feet. Okay, now the applying moment, so I'm gonna use O negative sign on top. So see, what is the applying moment? So if you want to find out the applying moment, you go back to the moment diagram, which is given here, right? And this is the negative moment, right? Applied negative moment. So that gives me a number of 225 kip feet, 225 kip feet. So naturally, MCR divided by MA, negative sign, that's 55.5 divided by 225. 55.5 divided by 225, so equal to 0.247, 0.247, okay? So how about cracking moment? Now this cracking moment we already calculated from this diagram, right? From this diagram, okay? From this diagram. So skip the details, right? I'm going to skip the details. So if you have the diagram, you can proceed to calculate that. That'll give you the 11366 inch to the power of 4. Okay, inch to the power of 4. Now, if you have a question how we got that, please practice a little bit following our instruction from last lectures. And if you could not get this number, we'll compare this number tomorrow on Tuesday office hours, okay? So I'll illustrate that Tuesday office hours, okay? And then with that, I get my IE1, okay, equal to 0.2473, okay? This is 17200, 1 minus 0.247 cube, and 11366. And this gives the final number 11450 inch to the 4. Now you wonder where that equation come from, right? So this equation basic is MCR divided by MA to the cube, and this is IG, plus bracket inside 1 minus MCR over MA cube, bracket here, and I crack. Okay, so that's the formula. All right. Okay, so you see here, I have one. Okay, why is that? Because this is the column, and this is the beam. Okay, so this is IE1, and this is IE2, moment inertia for both ends, and this is IEM middle, right? This is IEM middle, okay? So we just finished IE1, but IE2, since it's symmetric, they're the same, okay? And IEM is basically the positive moment, right? So this is the positive we just calculated before last lectures, okay? So with that, I have my whole equation laid out for me, right? So the I effective equal to half 0.5 of IEM, which is the moment inertia in the middle span, plus a quarter of IE1 plus IE2, IE2. Okay, so now bring the number in, have 50%, 0.5, IE middle, right? What is IE middle? So go back to see this number, it's 13340, 13340, so 13340 inch to the 4 plus a quarter of, now, since IE1 equal to IE2 in this case, symmetric, right? So this is 11450, which is this number here, and multiplied by 2. Okay, so now I got the final number is 123.95 inch to the power of 4. Okay, so now that is the effective moment inertia. That is the effective moment inertia. Okay, so finally, I can start doing the deflection calculation. So first thing first, I want to do instantaneous deflection. So instantaneous deflection, right? Instantaneous deflection. Okay, so what is my instantaneous deflection? So that is delta I, right? Delta I. So now I want to do delta I due to full dead load plus live load, So delta I, comma, dead load plus live load equal to 5 over 48, 5 over 48, top L squared divided by EI, L squared divided by EI. Here, bracket inside, which is M moment, and this is middle span, okay, mid span, okay, plus a 0.1, 10%, okay, M1 plus M2, this is end span, left end, right end, okay, left end, right end, okay. So that is the equation used to calculate the deflection. Now you may wonder where that equation come from, right? This equation you can find out from equation 918 in the textbook. 918 in the textbook, okay? So that's the equation commonly used for calculating deflections, All right, so now bring this number in. So I have 5 over 48. Span length is 25 feet. Converted back into inches is 12 inch per feet per foot. And square, don't forget square. And bottom here, the Young's modulus for concrete, this is concrete, okay? So that is 3,600 KSI, okay? And then EI, I got this number, this is IE, okay? Which is this number right here. So that is 12395 inch to the power 4, inch to the power 4. Okay, and then get this whole thing in, that is 162 kips feet. Where that 162 coming from, right? You go back to the moment diagram, and this is—
Could you slow down just a little bit, please?
Yeah, just a second, okay? So Sean, here's the moment diagram, 162 kips feet, okay? So I'm gonna get this copied down here. Let me try to copy it, okay. Okay, copy. All right, try to paste. Okay, so that's the moment diagram, right? So Sean, what do you mean by slow down? You want to go back or?
Oh, it's just going really fast.
Okay.
It's
8:15.
Okay, can you see this equations? All right. Okay, so let me quickly recall. So this equation for moment deflection, for calculated deflection here, okay, this 548, this equation right here, this is an existing equation from the textbook, 918, okay? This is standard equation. Now, we're not going to ask you to derive any equation from the exam. So if you, or homework, so if you were asked to calculate deflection, you can directly use this equation, okay? And this is for a moment diagram like this. So it's a distributed load moment diagram. All right, so as long as I have a moment diagram like this and with end moment and middle span moment, you can directly plug in this equation to get deflection, okay? All right, so this is 0.1 and M1 is the end moment, okay? The M1 is basically this number right here. This number right here, all right? This number right here. But one thing is slightly different is before, when I calculate my moment, you notice that I have 55.5 divided by 225, and the negative sign in front of it got canceled. The negative sign in front of it got canceled, okay? The negative sign got canceled. So there's no signs in my ratio here, right? In my ratio here. But if you go back to this equation right here, where I had to get moments plug into this deflection equation, there is sign, okay? So this M1 is negative 225 kip feet. And I have another moment, which is another 225 kip feet. So make sure I have the sign considered. So this is minus 225 feet, okay? Okay, so don't forget, right? Don't forget, I have signs, right? I have signs. Now, this is in terms of kip feet. I want to convert it back to inch, right? Inch and pounds, right? Inch and pounds. So this is multiplied by 1,000, multiplied by 12, right? So 1,000 multiplied by 12. And now I want to box this figure in. So this is not necessary. It just remind you. This is moment diagram. Okay. So carrying on this calculation, simply just plug the number in. I got this number to be a 0.295 inch. And let me just carry this from previously. Okay, that's the deflection, instantaneous deflection. All right, this is instantaneous deflection. Okay, instantaneous deflection. All right, okay. So I got the instantaneous deflection. Now this is dead load, DL, and live load, two components. So I'm gonna go back and see, actually the dead load, omega DL, dead load is 1.65, okay, kips linear foot. All right, and the live load from previous lecture is 3.3 kips per linear foot. Okay, so immediately I get a partition of the total deflection into the component caused by the dead load and the component caused by the live load, right? So now I have delta I instantaneous deflection caused only by the dead load equal to this d delta I dead load plus LL live load multiplied by a ratio, right? This ratio is W omega DL divided by omega DL plus omega LL. Okay, so this I actually have a 0.25 inch right here, and the top here 1.65, bottom here is 1.65 plus 3.3. Okay, so now I got the deflection for the dead load is 0.098 inch. Deflection by the dead load 0.098 inch. Okay, now then correspondingly the live load distribution, the deflection caused by the live load is delta I DL plus LL multiplied by omega LL divided by omega DL plus omega LL. So that is 0.9295 inch multiplied by 3.3 on the top and bottom here 1.65 plus 3.3. Okay, so I got this number to be a 0.098 inches. Oh, not again. I'm copying it down simply. Sorry about that. So it's 0.197 inch. Okay. Just short comments, right? Just a short comments. After I get whole deflection out, right? I realize that my live load has much bigger deflection than dead load. Okay? So basically saying the deflection usually is controlled by the live load. Okay? Okay. All right, good. Okay. Now, let me ask you this question. Well, apparently you're on mute right now, but if anyone cares to answer the question, here is the question is that what or where exactly this deflection is at, right? So we talk about this is the beam. Say, now we have almost like a fixed end. So it's gonna deflect, Let me use something like that. So where is the deflection at? Right? So I want you to keep this in mind. This deflection is at middle span. Don't forget, okay? This deflection is at the middle span. Now, you may ask, okay, so Bob, when we calculate the moment inertia was not only in the middle span, we do consider the contribution from two ends. Yes, but those are boundary conditions. We do consider them when we calculate the moment inertia for the whole beam, but when we actually calculate the deflection, it is at the middle span. Okay, all right, good. Okay, so this is instantaneous deflection. Okay, so how about long-term deflection? Okay, so delta equal to long-term, right? Equal to lambda delta I dead load plus delta I live load and plus a lambda delta I live load sustained. This means sustained. Okay, and lambda is what? Lambda is what? Lambda is a coefficient, right? And that is determined by epsilon divided by 1 plus 50 rho prime. 1 plus 50 rho prime. Okay, and now let's do some calculations, right? Now, first of all, this lambda here is regarding to a time, is a function of time, okay? So when it is a function of time, basically I want to write a time here, t, and the only variable in this equation that depends on the time is this epsilon on the top, epsilon at the top, okay? And we know that epsilon t, right? Epsilon t, right? For life of structure, for the entire life of structure, epsilon t equal to what? Equal to 2.0, okay? Basically, let me rewrite it better. So epsilon t equal to infinity forever, right? We assume our structure is gonna last forever, right? So this equal to 2.0. Now, if you confuse, so where does that 2.0 coming from, right? Where is that 2.0 coming from? Go back to our previous lecture notes. Now there was a drawing right here, right? And you notice that as my time approached to infinity, my coefficient yields at 2.0, okay? This is this equation right here, okay? Now in the exam, again, you don't have to remember the equation, but please prepare this figure, okay? Prepare this figure, include this in your crib sheet, okay? Include this in the crib sheet. All right, so now with that, I know I have the equation laid out and my c or epsilon on the top written as 2.0. Now the problem is, what is rho prime? Rho prime is the reinforcement ratio for the compressive reinforcement. That is AS prime divided by BD. AS prime divided by BD, right? Now AS prime equal to the area for compressive reinforcement. Area of compressive reinforcement. Okay, so what is AS prime? Now, don't forget, right? Don't forget again, let's scroll back to the structure drawing, we have here. And at middle span right here, right? At middle span right here, I don't have any compressive reinforcement. At middle span, I don't have any compressive reinforcement. AS prime equal to 0. AS prime equal to 0. So what we're gonna do here is, I'm gonna say, now, consider this, right? Since at middle span, no compressive reinforcement. Therefore, AS prime equal to 0. AS prime equal to 0. So rho prime equal to 0. Now with all these parameters, I can now say lambda equal to 2.0 plus 1 multiplied 50 multiplied 0. And this gives me a 2.0. So with this factor, lambda equal to 2.0 determined, I can plug back into the equation, find out my long-term deflection for the partitions, right? For the partition, so that is 2.0, bracket inside, the deflection caused by the dead load is 0.098 inches, right? This number is right here, okay? 0.098 inches, plus a live load, which is 0.197 inches, deflection calculated previously, and plus another lambda multiplied by 0.197 inches. This is the delta I instantaneous live load, okay? But the equation right here is asking for sustained. And recall the problem said there are 20% of the live load sustained. So multiply 20%, okay? So now my final number yields at 0. Oops, sorry, I don't know why this is. Hold on, okay, okay, so that's good. So my final number deflection yields at 0.472 inches. Okay, 0.472 inches. 72 inches. Okay. Okay. All right. So now, finally, I got my long-term deflection. Long-term deflection. Okay. This is the long-term deflection. All right. So now we're done with serviceability. We're done with serviceability. Okay. So here is the long list of what we had did before. So quick review, right? Quick review for this problem at hand. What we did, right? We first checked out the gross moment inertia for a uncracked section, right? And for the uncracked section for positive moment, right? And then essentially we said, since it's I-beam, uncross section, right? Uncracked, right? I'm gonna take this whole section, right? Take this whole section. Then I got the ICR positive moment. So I assume the compressor is within the flange, and then convert the steel into concrete NAS and calculate the moment inertia this way. And we also calculate ICR for negative moments. Now the compressive zone is bottom here, and then the reinforcement at the top will be the tensile reinforcement. So converting to NAS, right? And then we proceed with calculating the IEM, which is the effective moment inertia at middle span. Effective moment inertia of middle span. To calculate effective moment inertia at middle span, we need several things. We need the cracking moment, which can be calculated from MCR, which is FR modulus rupture multiplied by IG divided by YP. We need apply moment from moment diagram, and we got a ratio, and we plug in to get this moment inertia, effective moment inertia at the middle span, okay? And then we calculate for the negative region, right? And slight difference in terms of the negative region, we have to invert our beam to calculate the compressive zone at the bottom here, okay? Then we proceed to do the same thing to calculate the moment inertia for the negative region. And then we got both the middle span and the two ends in terms of moment inertia, right? We bring this equation, plug them in to get effective moment inertia, right? And then we proceed to calculate the deflection. And when I calculate deflection, I use the equation that from textbook, okay? From textbook, and you can continue to use this one in your exam homework, all right? And once I calculate the total deflection, I separate them in terms of deflection caused by the dead load, deflection caused by the live load, okay? And keep in mind, all the deflection we're talking about is at middle span, Then I use this equation to calculate the long-term deflection. And to calculate this long-term deflection, I need a coefficient lambda, which is a function of time, okay? Usually for time, for life, right? For structure with life design span, right? We assume C or epsilon at the top equal to 2.0, and rho prime is the compressive reinforcement. In our case, there's no compressive reinforcement at the middle span, so I have 0 for rho prime. But in specific case, right, if you have compressive reinforcement, you do have to put that into consideration, okay? And then I bring the whole equation, the collapse gets my final long-term deflections. Okay, so now we're done with all the serviceabilities. I want to pause for a second and ask you guys, are there any questions regarding to this? Any questions? Anything that is unclear? Anything, guys, anything? Any questions? Date and time is the final. The final is supposed to be on the 11th, I think, for that week. And I'll find out a specific time from the registrar, and we'll release next week. Okay, so you have 2 weeks, roughly two and a half or three, less than 3 weeks, I would say, to study for it. Okay. All right. Any other questions about the content of lecture, about the serviceabilities? We'll talk about the final a little bit more by I would say end of this week or Monday. Okay, Thursday and Monday we'll talk about the final a little bit more. Okay. Any other question on the serviceability? Now, serviceability is a crucial component for the final exam. So guaranteed there will be one problem at least to calculate deflections, because this is a very good problem. I can have a section to test how to calculate the transform sections and then ease into deflection calculations. So there's definitely one problem on that. 12 something a.m. Yeah, Kristen, that might be the case. But let me double check with the registrar office. Okay. All right. Now, I wouldn't sweat right now with specific content and final exam. I haven't made them yet, but I would be more concerned how to calculate the serviceability part of the exam. Okay. Now, the one with lab is tested already, so we do not necessarily have them as a calculation of finals. Now, the most important thing for the final is serviceability, column design, and the development lens. And we will talk about at the end of the lecture. So right now for the serviceability, are there any other questions? Anything that is not clear from serviceability? Okay, are we good here? All right, so I will release the homework on serviceability today, okay? As usual, you have a week to turn me in. Yes, column design is definitely gonna be in the final, which will start right now, okay? We'll start right now. We'll finish the column design by next Monday, hopefully, okay? Column design is definitely gonna be in the final, okay? That's one of the important components, okay? All right, so I guess we're good. So let me start a new notes on the column design, okay? So this is lecture Monday. Okay, this is column design. Okay, column design, okay? All right, so learning objectives, right? Learning objectives. What are we going to do with column design? So learning objectives. Okay, so of course, the overall goal is to be able to design a concrete column. Design a concrete column. Okay, and also we need to determine or distinguish, tell the difference, distinguish, okay, between two major categories of columns. Two major categories. Major categories of columns. Okay. All right. And then we also need to compute the axial strength of a concentrically, which we'll talk about it, okay? Concentrically. Loaded column. Okay. And you find this in a textbook, in chapter 11, 11.1, 11.2. Okay. 11.1, 11.2. So these are the objectives. These are the objectives. Okay. All right. So axial compression members. Okay. So in terms of compressive members, let me draw this in the middle. That is the central topic for concrete design. Okay. So you think of it, right? What are we dealing with every day in daily life, right? We're talking about the bending, which is flexure, and we talk about the shear, and those are all for beams, right? So one way beam or slab, right? So the beam and slab, you have moment to consider, you have shear to consider, and then finally you need a column, right? And the column is all included in this compressive members, Okay. Now I want you to think of this picture, right? So I have a compressive member, right? So usually this is what a column would look like. So I have this compression force, but also sometimes I can have a eccentricity. So that means I have a bending moment. So the compressive member can be divided by the type of deflection. So one is called with, and the other is called without bending. With and without bending. With and without bending. Okay. So all these compressive members, right? What are those compressive members? So for example, I have arch. Okay. I have ribs. right? So you've seen this arch before, right? For example, this is the arch, and this is the doorway, and they're in compression like that, right? And I have wall. Sometimes I have walls, vertical member, okay? I also have shells, right? So for example, if you go out to see a stadium, and there's gonna be arc on the outside, and actually they're in compression, right? They're in compression. I have truss members, which if you go out a bridge, for example, I have a typical truss members, right? And that is in compression, okay? I also have frame members, right? And you know all about it, right? Frame, for example, like this, okay? And I have compression, and I have columns, right? That is the central topic of our lecture this week, columns, vertical members, columns, okay? All right. Now, for columns, I can further divide them into the following subcategories, right? I have column with longitudinal bars. I have columns with longitudinal bars plus lateral ties. Okay. So these longitudinal bar with lateral tie, if I see a cross section, these are longitudinal bars, right? Cross sectional view. And I have ties like this. Okay, this is the one type of column. I have the other ones, longitudinal bars plus spiral. Okay, so that means if I see it, so it's almost like a circular, and I have bars all around it. I have bars all around it. Okay, so that's another thing. And then we also have a composite. Also have composite member with structured steel. That means I have a section like this, and I have H-beam. I have H-beam, for example, steel inside, okay, inside, right? Now, for our purpose, right, we're gonna talk about this, and we're going to talk about this, okay? So we'll discuss this only. Okay, we only discuss column with ties, with square stirrups that has openings, okay, on the left, ties, okay? And we also discuss column with spirals. Okay, all right. So these are a general classification of compressive members and also columns, right? So we're focusing on the ties and spirals, spirals. Okay, so moving on, right? Again, a finer definition of columns, right? So columns, what are those columns, right? So first of all, columns are vertical members. Columns are vertical members, okay? And then carry loads. Carry loads, right? Vertically, right? Of course, vertically, but mainly in compression. Use red, highlight that. In compression. Okay. So keep in mind, columns typically bearing compressive stress. Okay. But also we don't forget, we cannot forget there's also something else, right? Consider as bending. So bending might occur about one or both axes. Right? So simply put, if I have a column like this, right? Now from basic mechanics and materials, combined loading, combined loading chapter, right? So I have, if I have a off-center load, right? I may have moment in this way. I may also have a moment in that way. So if this is x-axis, this is y-axis, I can have both my and mx, my and mx. Okay, so I may have bending. All right. So determining on these conditions, right? On these conditions, I can further divide my columns, right? My column into two categories. And one is short columns. Okay, short columns. Okay, so I want to say for the short column, you mainly need to consider compression, right? Only compression is considered for short columns because there's not much bending, all right? And then there's another category, it's called longer or slender columns. Slender or long columns. Okay. Now in this case, in the slender columns, right, we need to consider what? We need to consider both compression, bending, and possibly buckling. Okay. Considering mainly the buckling. Okay. All right. So I think this is a good stopping point. We're gonna stop here. All right. But now knowing that in our lecture, we're mainly gonna consider these two, the compression and the bending, So the buckling, not focused in our lecture, not focused in our lecture. Okay. All right, so I'm gonna stop here today and I'll upload the notes and the video to the channel as well. So please watch them. And Tuesday, tomorrow, let's go over some of the problems in serviceability, okay, for the homework. And I'll upload the homework today. All right, so if there's any other questions you wanna ask about, any other questions? Okay, well, if not, we'll meet tomorrow, 2 o'clock in office hour, okay? 2 o'clock office hour, all right? Okay, so I'll see you then. All right, thank you very much.